Hi, I'm Scott McLean from TranceMusicMastery.com, and this video is Anatomy of Sound. In this video, we're going to explore answering the following questions. What is sound? What are its basic properties? What are harmonics? And how do harmonics relate to four basic waveforms? And at the end, we'll begin answering the question, how to synthesize a sound. So first and foremost, what is sound? Well, I'm sure all of you are familiar with this. It's a physical phenomenon, and it's also a perceptual phenomenon. It's a physical phenomenon in the sense that it is a vibration of gas, liquid, or solid. An example, sound in air, the ocean, and sound moving through concrete walls, for example. And it's a perceptual phenomenon in that it requires the human hearing system. The ear senses sound vibrations, and the brain perceives the incoming vibrations as having three basic properties: loudness, pitch, and a concept called timbre. All sound can be expressed mathematically using a combination of one or more sine waves oscillating at various frequencies. So you might be wondering, what does oscillating mean? Okay, well, oscillating basically means repeating or cycling between two or more values. A simple example would be a blinking light can be described as oscillating between on and off. Well, with respect to sound waves in air, vibrating air molecules result in air pressure oscillating between two values. It hits a maximum positive pressure and a minimum negative pressure. So it's oscillating between the maximum and minimum. The ear senses this oscillating air pressure, and the brain perceives the oscillating air pressure as sound. So another question might be, well, what is a sine wave? Okay, well, a sine wave is a mathematical concept. This can be used to represent oscillating processes, in other words, something that repeats over time, like sound vibrations. So here's an example of a sine wave, and in this slide I'm showing one property of a sine wave, which is called amplitude. And I discussed some of this in one of the videos in the free series that you may have seen. The amplitude of a sine wave is shown in this slide by the green arrows. Okay, so it reaches a maximum of +1 and a minimum of -1. Now, a sine wave also has a cycle. In this case, I'm showing one complete wave cycle of a sine wave, shown from the start of the wave at the green arrow on the left, reaching the end of the wave cycle, the green arrow on the right. What is frequency? Well, frequency is the number of times something repeats over time. And in terms of a wave, frequency is the number of times the wave completes a wave cycle during 1 second. So frequency is expressed in units of hertz, or Hz. Example, a 100 hertz wave completes 100 wave cycles per second. So we can have waves at different frequencies as shown by this slide. So here we have one wave shown by the red sine wave. Okay, that completes one wave cycle. And then in the same amount of time, the blue sine wave completes one wave cycle and a second wave cycle. So that brings up the concept of the frequency spectrum. The range of human hearing spans a spectrum of frequencies from 20 hertz, which is a low, very low frequency, up to 20,000 hertz, or 20 kilohertz. To visualize the frequency content of a sound, we can use a spectrum analyzer, and it displays a graph of level, in other words, the amplitude versus the frequency. So here's an example of a spectrum analyzer showing frequency versus level. And here we see multiple frequencies within a sound at various levels. So there are basically three perceived properties of sound: loudness, pitch, and timbre. So loudness is really a function of the amplitude. The brain perceives sound waves oscillating with larger amplitudes as being louder than sound waves oscillating with lower amplitudes. It's typically expressed in units of decibels, or dB. Loudness can be measured physically using a sound pressure level meter, or SPL meter. And we can visualize it in a DAW using a level meter as an indicator of the signal level, which generally would correspond to the overall loudness of the signal. So here's a slide showing two different sounds, or two sine waves, at different amplitudes. So sound 1 is oscillating at a higher amplitude, in other words, air pressure, and the brain will perceive it to be louder than sound 2. Now we come to the concept of pitch and how it relates to frequency. It is related to the physical property of frequency, but it's not quite the same thing. The audible portion of the frequency spectrum can be divided into what are called octaves. Okay, and if you're not familiar with the concept of an octave, basically a frequency that's twice that of another is said to be one octave higher. Okay, so doubling the frequency goes up one octave. All right, and if we take half of a frequency, then we've gone down one octave. So here is the frequency spectrum drawn on a line, and we can start with octave 0. That's pretty much anything below 31.25 hertz. And then between 31.25 up to 62.5 is octave 1. 62.5 up to 125 is octave 2. If we go from 125 and we double that to 250, that spans octave 3, and then octave 4, and so on, okay, all the way up the frequency spectrum. So if we look at 500 hertz, for example, 500 hertz is one octave higher than 250 hertz. And 500 hertz is one octave lower than 1000 hertz. So the next thing to look at is this notion of lower and higher pitches. Okay, higher note pitches correspond to higher frequencies, and lower note pitches correspond to lower frequencies. And now we can define what pitch really is. Pitch maps musical notes to the frequency spectrum by tuning each note to a specific frequency. All right, so we have C0 through B0, and then the notes C1 through B1. The number indicates the octave that the notes are in. So C4 means the note C within the fourth octave. In other words, middle C, which would be tuned to 261.62 hertz. And C5 means the note C within the fifth octave, which would be double the frequency of middle C, which would yield a frequency for C5 at 523.24 hertz. Now, each octave is divided into a sequence of 12 semitone pitches. So C4 would be at 261.62 hertz, and then we'd have C sharp or D flat, and then D4, and then it's sharp, and then E4, F, F sharp, G4, G sharp, A4, A sharp, and B4. That would be 12 semitones within the octave, the fourth octave. I've kind of depicted it like the notes on a piano or keyboard, just to give you a reference there. Then you'd have those same notes mapped into each of the octaves to form the overall, to span the entire piano keyboard, for example. Now we come to the concept of timbre. Okay, this is pronounced timbre or timbre or timbre. Okay, it just depends on how you want to pronounce it. I prefer timbre. It's also known as tone quality or tonality or tone color or texture of an individual instrument sound. And timbre is what makes a sound distinct from another sound played at the same pitch and loudness. Okay, this is important. So if you have two sounds, each one is at the same pitch and loudness, timbre is what allows us to distinguish one sound from another. So for example, a piano sound versus a pad sound. If we had a piano note playing middle C and we had a pad playing middle C, then we would be able to distinguish these two sounds from one another, or these two instruments from one another, based on their difference in timbre. Another example would be a lead sound versus a vocal sound. Okay, so if we had a lead sound playing middle C versus a vocal sound playing middle C and at equal loudness as well. So they have to be at the same pitch and the same loudness. The thing that lets us distinguish the lead sound from the vocal sound would be the differences in their timbre. So now what is that specifically? What contributes to timbre? Well, if we look at complex sounds, any complex sound typically contains multiple sine waves oscillating at different frequencies. So by any complex sound, that's the human voice, any of the synthesizer instruments, pretty much any sound other than a simple sine wave, okay, would be considered a complex sound. Well, if we look at the different types of frequencies present in a sound, they are important and are responsible for our perception of pitch and timbre. So the different types include the fundamental frequency, which I'll define in a moment, overtones, and harmonics. So the fundamental frequency, also known as the fundamental, is defined as the lowest frequency present in a sound. Okay? So the brain perceives this as the pitch of the sound. So if we look at this and we graph frequency versus level, and we look at a complex sound in a spectrum analyzer, we can see that the complex sound has many frequencies present within it, and the lowest frequency present within it is the fundamental frequency. Next, let's talk about overtones. Sounds other than pure tones, in other words, complex sounds, also contain frequencies higher than the fundamental frequency. Okay, we call these frequencies overtones. So if we look at these in a spectrum analyzer, we can see the fundamental frequency is the lowest frequency present in this sound, and all the other frequencies that are present in the sound higher than the fundamental are called overtones. This brings us to another concept called harmonic content of sound, or harmonics. Some overtones occur at frequencies that are integer multiples of the fundamental frequency. We call these overtones harmonics. The harmonics present in a sound and their relative levels are largely responsible for the timbre of a sound. And this brings up the concept called the Harmonic Series. The sequence of frequencies that are integer multiples of the fundamental frequency are known as the Harmonic Series. So 1 times the frequency, that is the fundamental frequency. Okay, 2 times the frequency is 1 octave higher than the fundamental frequency. 3 times the frequency, 4 times the frequency, 5 times the frequency, etc. That is known as the harmonic series. So, for example, if we assume the fundamental is 110 hertz, okay, then we'd have a fundamental at 110 hertz. 2 times the frequency would be 220 hertz. 3 times the frequency would be 330 hertz. 4 times the frequency would be 440 hertz, and so on. Okay, let's take a look at harmonic content of sound. So here we've got the fundamental frequency, and it looks like it's around 110 hertz. Then we go up and to the next one that's present, that looks like it's around 220 hertz. Then we go to the next one, that's 330. Then the next one, 440, and so on, all at integer multiples of this fundamental frequency. Okay, this would continue all the way up. That brings us to the concept of 4 basic waveforms. Harmonics give rise to 4 basic waveforms: a sine wave, triangle, saw, and pulse wave. For example, a square wave. The sine wave contains only the fundamental harmonic with no overtones. So it contains just that fundamental, or the fundamental frequency. In this case, the fundamental is 110 hertz. So this would be a sine wave at 110 hertz. Saw waves contain all harmonics. So that's the entire harmonic series. That's what a saw wave looks like on a spectrum analyzer. So we see that the fundamental is at 110 hertz. The next one up is at 220. The next one up would be 3 times the fundamental, or 330. The next one up is 4 times the fundamental, or 440, and so forth. And also notice that they're not at the same levels as the fundamental. Each time we go up in frequency, or each subsequent harmonic is at a lower level than the previous one. And the relative levels are important as well in defining the particular waveform, as we'll see in the next few videos. Okay, let's look at a square wave. This contains only the odd harmonics. So the fundamental, the third harmonic, the fifth harmonic, etc. If we look, we see the fundamental. If we went up twice the fundamental, we should see something at 220, but we don't. It's missing. Okay. Then we go up to 3 times the fundamental. We end up at 330, so we see the presence of a sine wave there. And then we go up to 440, and it's missing, so we don't see that harmonic. Then we go up to 5 times the frequency, the fifth harmonic. We see that at 550. 660, we look for it there, and we do not see the sixth harmonic. Okay, so this only contains odd harmonics. And then the triangle wave contains only odd harmonics, but higher harmonics are at lower levels than the square wave. Okay, so we see it drop off much more quickly than we did in the square wave. Okay, properties of sound are dynamic. So loudness, pitch, and timbre may change over time. So if loudness were changing periodically, that would be an example of tremolo. Another example would be a change from loud to soft. Pitch, an example of that, vibrato. Another example would be a pitch riser. Timbre changing dynamically over time. An example of that would be a change in the sound from a warm sound to a bright sound. So just to review quickly what we've covered so far, we've examined the basic properties of sounds. We've covered the fundamental frequency, harmonics, and looked at how the harmonics contribute to the 4 simple waveforms. Well, the next question would be, well, how to synthesize a sound. Another way of asking this question is how to generate and dynamically modify the basic properties of sound, which would be loudness, pitch, and timbre. In other words, harmonic content. Well, we're going to do that in the next video. We're going to begin answering the question, how to synthesize a sound, by exploring the process of synthesizing basic waveforms by combining harmonics. So if you've had any questions on this video, please leave those below as well as any comments. I'll see you in the next video.